And at the beginning, I need your help. I want answers from you because we are studying a very important topic in the inorganic chemistry regarding the bonding. What is the topic or what is the point? Point is hybridization. Already 2 lectures I invested on this hybridization. It is our third lecture. Now with the help of you, let me revise the things. At the beginning, we discuss sp hybridization. What is the example for sp hybridization?
BCl2.
BCl2, BF2.
Right. Any beryllium and 2 halogens. Very fine. Second hybridization is sp2. Please furnish the example.
BF3, BCl3.
BCl3.
Brilliant. Very good. Third hybridization is sp3.
SiCl4.
CH4.
Yes, very good. SiCl4. But what is expected from you? The central atom you have to find out its electronic configuration, then the mixing and recasting of the suitable orbitals, and the geometry of the hybrid orbital. That hybrid orbital interacts with the peripheral atoms, where unpaired electron in the hybrid orbital and unpaired electron in the peripheral atom will lead the bond. Yes. In addition to that, I discuss Sp2d hybridization. Yes. Example, please.
PCl5.
Yes, 5 bonded phosphorus, PCl5. And as a homework, I ask you to study Sp3d2 hybridization. I want to know example from that.
SF6.
SF3.
SF6, because 6 bonds are there, no? SF6. If you note, when 2 bonds are there, we have discussed beryllium, which belongs to which group? Second group. 2 bonds, second group. Very interesting. But if you come to boron, can anybody answer boron belongs to which group?
Group 3rd.
Right. It is from group 13, but in between whichever the D block elements are coming, transition series elements are there, those are 10. If I do not consider those transition series element, then certainly it will be of the 3rd group. Indirectly. Previously the names were likewise only 3rd A and 3rd B, and because of that here 3 bonds are there. 3 chlorine atoms are surrounding the central boron atom. Now I want the answer from you. Silicon belongs to which group?
Group 14.
Yes, group 14 means it is as good as it is a 4th A group, and due to which here 4 chlorine atoms are surrounding the silicon. Yes, further, phosphorus belongs to which group?
Group 15.
15 or 5.
Yeah, 15. So old nomenclature 5A, but whatever these are nomenclatures are there, 2, 13, 14, 15. These are the new ways of representation of group number. Likewise only we have to proceed. But one interesting thing that I am bringing to your notice, the sulfur belongs to 16 group. So here 6 chlorines are there. Phosphorus was belong to 15 groups. So 5 chlorines are there. So number of peripheral atoms are decided on the basis of group number. Why it is so? Because group number depends upon valence electrons. Electrons in outermost orbitals. Here see, in case of the beryllium, 2 electrons are there. So it's the second group. Here 3 electrons are there. 3 chlorine atoms surrounding. 4 electrons are there. 4 chlorines are surrounding. 5 electrons are in outermost orbitals. So 5 chlorines are surrounding. Here 6 electrons are in outermost orbitals. So 6 fluorines are surrounding. So number of peripheral atoms are decided by means of the total possible or available electrons in the outermost orbitals. Up to your concept clear? Is it clear?
Yes, sir.
Yes, sir.
Only 2 answers I am getting.
Yes, sir. Yes.
Yes, sir.
Yes, sir.
Very good. But bad because unless
Yes,
until I ask you to answer, you are not answering. Okay, fine. Students, today we are discussing very interesting hybridization, and about which a proper study material you may not get. And if you generally search on the internet, the wrong informations you will find. About sp3, you know that sp3 can lead which kind of geometry? Tetrahedral geometry. How can I represent that tetrahedral geometry? 1 bond from up down, second bond as like a tripod stand remains, 3 pillars should be there, 3 rods should be there. Likewise here 1, 2 and 3. So you can consider one tripod stand, and above the tripod stand how the beaker, crucible or conical flask you keep, no? Likewise one more bond is there. It is our tetrahedral molecule. Number of bonds are 4 and hybridization involved here is Sp3. My point of interest is number of bonds and hybridization. Other than this Sp3, can anybody answer which hybridization possible for 4 bonds? Yes, 50% answer I had given. You have to complete this answer. 4 bonds.
DSP2.
Brilliant answer. DSP2. And geometry for that will be, yes, anybody can attempt. I had given the abbreviation for that. Describe that.
Square planar.
Right. It is a square planar. So 4 bonds, how can we arrange? 1 bond at the corner of one square, second bond, third bond, and fourth bond. So likewise a square arrangement you have to understand for DSP2 hybridization. Here also 4 bonds are there. In addition to that, to your surprise, which portion is not covered generally, one more hybridization possible, that is Sp2d. And geometry possible, can anybody guess? Or coordination number 4 or 4 bonds, only 2 possibilities, one tetrahedral, square planar. So here also geometry possible is square planar, but hybridizations are different. One is Sp2d, other is DSP2. So 4 possibilities are there. How does molecule decide the hybridization? That we are learning. Purpose of hybridization. Why the molecule or the central atom undergoes hybridization? What may be the purpose of hybridization? Okay, don't answer about hybridization, just only answer for the question, why do molecules react? Why do they react with the various number of the atoms? What is the purpose of reaction?
To form bond.
Yes, brilliant answer, to form bond. But can you answer why bond formation necessary? What is the purpose of bond formation? See, we also remains with our friends. We have the bondings with the friends, relatives and many others. So there is also the bond. How can we understand that bond? Likewise, atoms and molecules also want to form a bond. Atoms and molecules also want to have a friendship. Why do we have the friends? What is the need of the friendship? That's the question that I'm asking. What's the need of the bonding?
To stable the energy.
Brilliant. Purpose is happiness or purpose is stability. By doing so, the molecule or system or chemical governs a very important thing for which molecules and atoms die. That's a stability. They want stability, and there are the many ways by which you can get the stability. Means you can play with your friend on the ground, means cricket you can play, or the various games you can play on the ground. There also a friend circle, a friendship remain. Along with friend you can study. So there are the different ventures by which you can understand the friendship. Likewise, the stability or happiness molecule or atom can get by means of the many ways. And out of that, bond formation is a one aspect. Certainly it is. But bond formation, if it has to occur, then there also are the different methods. So via hybridization, molecule can govern the stability. What is that hybridization? In hybridization, which steps are there? Now help me. I want answer from you because you are studying hybridization topic. What remains in hybridization? Which steps do remain present during hybridization? Yes, I want answer from you because you have discussed the various molecules.
Example. Yes.
Yes, example is the one. Okay, example you have considered. After us, what you do?
Line structure.
Electronic configuration you represent. Okay, after us, what you do?
VBT.
I could not hear clearly. Repeat, please. For example, if I consider carbon, atomic number is 6, its electronic configuration 1s2, 2s2 and 2p2. If I have to represent that electronic configuration in the block diagram, then I can represent only one block for the s orbital. 2 electrons are there. And if I consider the p orbitals, three orbitals are there, px, py and pz, but I am with only two electrons. So it is expected that carbon should form two bonds because of two unpaired electrons, but it is not the reality because carbon undergoes hybridization. My question is, what actually hybridization mean? Which steps are involved in the hybridization? So what you do before mixing?
Excitation of electron.
Basis of PBT.
No. Before mixing, you are doing something. See, I am showing by arrow.
Excite.
Yes, hybridization involves excitation if it is needed. Excitation of electron. After excitation of electron, suppose if this electron goes outside, means in the last orbital, then after excitation, carbon atom will undergo what? Which step it is? To that we are saying it is sp3 hybrid orbital or sp2 hybrid orbital or sp hybrid orbital. Yes. What is that? After excitation of electron, next what we do? What is that? This s orbital and p orbital, they combine. What we say for that? This one s orbital and three 2p orbitals are combining. To the combination, we say one word.
Sigma bond.
No. Okay, I help you. The word starts from M. That 2s and 2p orbitals combine, to that we say the word starting from M.
Mixing of orbitals.
Yes, I was expecting that. Mixing. After mixing, what happens? Recasting or redistribution. Means whatever the orbitals are mixed, they are aligned depending on, very interesting thing it is, depending upon peripheral atom actually, and depending upon the need of the atom, means how far stability it is going to govern by doing so, and accordingly arrangements will be there. Because if you see s orbital, it is spherically symmetric. If I have to represent the s orbital, then I can represent the s orbital as a sphere. It is spherically symmetric, means from all direction it has the equal justice. But if you consider the p orbitals, then p orbitals are perpendicular to each other. If I consider it is a px orbital, it as what? Py orbital, and perpendicular to these two, you can consider a pz orbital that I am not representing. My point of interest here is separation, angular separation between px and py. Can anybody answer what is the angle between the px orbital and the py orbital? This angle?
90 degree.
Yes, 90 degree. S orbital spherically symmetric. P orbitals have 90 degrees separation. But if you know the bond angle in sp3 hybrid orbital, yes, what's the bond angle in sp3 hybrid orbital? 1, 0. Yes, I need your help.
9.5.
9.
Yes, 109 degree 28 minutes, or one can say 109.5 degree, because 1 degree means 60 minutes. Here it's a 28. 28 means almost 30, near about 30. So for 1 minute, if we say 1 degree, for 60 minutes, if we say the 1 degree, then for 30 minutes, we can say it is a half degree. So I represent it here 0.5, 109.5 degree. Yes, students, are you following this? 109 degree 28 minutes or 109.5?
Yes, sir.
Yes, sir.
Yes. So p orbitals
Yes, sir.
basically are with separation 90 degree, but in case of tetrahedral molecule, they have to separate by that angle, means there should be recasting and redistribution about the p orbital, means somewhere they are burdened to change the shape, change the angle. So somebody is forcing them, and that forceful things that atom never do unless and until the future is bright. What do you think? Are you enjoying the study? Do you like to study, especially chemistry? Yes or no?
Yes, sir.
Oh, very good.
Yes, sir.
Okay, exceptions always do remain. Exceptions.
Yes,
Okay. Generally, what happens? Study
Yes,
means
sir.
it's somewhat the boring thing. Even though it's a boring, you do that. Even though it is not interesting, you do that. Even though you are not so that much enthusiastic or happy now, you do that. Why? Because you expect and you believe that by investing the time in study now, the future is bright. In future, you will get the satisfaction, you will get the happiness, and therefore you are doing this task even if you do not agree. Molecules or atoms also are with the same mentality. Actually, p orbitals are separated by 90 degrees. So they have to change there, means they have to distort, they have to do some kind of upgradation in order to get that 109 degree 28 minutes. And means some energy needed to have that hybridization, means some investment somebody has to do. While doing business also, we spend some money at the beginning, we invest money. Why we invest money? Because we are sure that that money will grow later, and therefore we invest the money. Likewise, carbon has to invest the, I'm not saying money, but carbon will invest its energy. May it get energy from surrounding, but it has to invest energy. For what purpose? Our main thing, that's a hybridization. So first energy is invested, first money is invested, business starts. It's the here business of hybridization. After hybridization, then the surrounding atoms are welcome. Surrounding atoms form the bond, and when bond formation takes place, now I want your help. When bond formation takes place, then energy will come out or energy will be needed. Means if I consider silicon as a central atom, and that silicon or carbon which is forming bond with the 4 chlorine, after formation of these 4 bonds, energy will come out, that E will come out, or energy is needed. I want your help. My question is, during bond formation, what happens? Energy comes out or energy needed?
Energy comes out.
Yes, energy comes out, is exothermic. Because to break a bond, if you have to give energy, then during formation of bond, certainly energy has come out. See how the business mind that atoms remain with. Energy is invested, means used, utilized, absorbed. For what purpose? For hybridization. After hybridization, the bond formation takes place. And after bond formation, that whatever the invested energy is there, not necessarily that, more than that, more investment, more amount than investment, more energy than investment comes out. That's a profit. That's a business. Therefore, even though it is a troublesome for p orbital to align in tetrahedral way, p orbital does that. P orbitals do that process. Reason? Happiness in future. Reason? By bond formation, whatever the investment is there, that will be returned. And molecules are so perfect businessmen that they will not invest the money unless and until there's a profit. Means by any means. Before that, is this point clear?
Yes, sir.
Yes. By any means,
Yes, sir.
energy needed for hybridization, energy is needed, is more than energy which comes out after bond formation. Means what? Here investment is more and output is less. You are investing lakh rupees and output is 90,000. Business is in loss. Atoms, molecules don't do a business which is in loss. Always they remain profit. So such a business they will not do. What is expected? Energy for hybridization, energy needed for hybridization should be less than the energy released during bond formation. It is a business mentality of the atom. Carbon, after sp3 hybridization, more energy is necessary for that, but investment is done because after that sp3 hybridization, whatever the 4 bonds are obtained, those 4 bonds are giving the more stability, and because of that, the CH4 molecule, or here whatever the example I consider, that's SiCl4 molecule forms. Yes, students, is the business mind of the atoms or molecules related to hybridization? Is it clear?
Yes, sir.
Yes, sir.
Yes, sir.
Yes.
Now let us see our new hybridization. My purpose to explain here is a 4 bonded hybridization. 4 bonded hybridizations are sp3 that we have discussed. But when can sp3 occur? When can Sp2 occur? Or Sp2d occur, that we have to study. Many say, means if you go to the internet, you will find DSP2 and Sp2d are the same kind of the hybridization. No, they are not. The orbitals involved are what the different. My point of interest here is to describe this Sp2d hybridization. Very important hybridization. With example, I describe it first. Then you will understand why that geometry is a square planar and why square planar geometry is not there for sp3 hybridization. So let me describe it one by one, stepwise. In between, suppose if question comes, you are free to ask question, but I suggest you let me complete the discussion and afterwards you can ask a question. The example that I want to consider is copper complex. Copper complex with coordination number 4. Here coordination chemistry is used. The square bracket indicates there is a coordinate bond formation. Here ammonia is a ligand and the copper is a metal ion. Ammonia carries no charge. So copper will carry +2 charge. A charge on this copper here is +2. Atomic number of copper is 29. If I have to write its outer electronic configuration, then argon, where 18 electrons are involved. After argon, the 4s orbital will start to begin. That's a potassium. After 4s, 3d orbitals are there. It is expected that it should be the 4s2 3d9, but it is not. If I have to write it in terms of the orbital arrangement, because hybridization is mixing of the orbitals, energetically 4s orbital may be the suitable, but that electronic configuration I represent as argon 3d and 4s. See here, only 9 electrons, means it needs only 1 electron to complete that d orbital. So preference is given to that d orbital 3d10 and then the 4s1. It is electronic configuration for copper atom. But my point of interest is an ion present in that molecule, that is Cu+2. Cu+2 electronic configuration, if I have to write, then I have to remove 2 electrons. Then a bit natural, I will remove here first electron from the 4s and one of the electron from the 3d. So its electronic configuration will be argon 3d9 4s0. After this 4s0, one more orbital is there. Electron may not be there, but we need to consider that. That is 4p orbital. No electrons are there in that 4p orbital. Its electronic configuration for central metal ion, that's a copper +2. I represent it in terms of the block diagram. If 3d orbitals I have to represent, then 5 orbitals 1, 2, 3, 4 and 5. 3d orbital, then 4s, then 4p. Let me represent those orbitals. Let me fill electrons within it. 9 electrons are there. First, second, third, fourth, fifth, sixth, seventh, eighth, and 9. In 4s and 4p electrons are not there. So one can expect this unpaired electron is there. So it has no use, that orbital has no use for the hybridization. So one can expect, it is possible that there will be the interaction between this 4s orbital and 4p orbital. So there may the possibility of sp3 hybridization. It is one possibility, but practically it is found in case of the copper ammonia complex, sp3 hybridization is absurd. Actually, valence bond theory, Linus Pauling theory for copper ammonia complex, when was applied by Linus Pauling only, then he did one interesting thing which is absurd, which is wrong. What he said, the electron whichever present in this last orbital, this electron will excite. Where will the electron go? Electron will go in this one last 4p orbital, due to which what will happen, the vacant orbitals, that one is d orbital, then is s orbital and 2 p orbitals, so that the hybridization type will be dsp2. sp3 means tetrahedral structure and dsp2 means square planar structure. And practically it was found that copper ammonia complex was square planar. So whatever the Linus Pauling said, people thought that he is correct. But whatever the explanation he had given is just only to prove his theory correct. What he is saying, electron from this one of the d orbital excites to a p orbital, that's a higher energy level, which is impossible practically. If it has to excite, then electron will completely go out. So copper plus 2 will form copper plus 3, which is not possible. That impossible thing that Linus Pauling has understood or accepted and accordingly attempted to describe his theory. Yes, students, are you following the way with which I am proceeding now?
Yes, sir.
Yes, sir.
Yes, sir.
Yes. Any doubt in between? Any student remains with doubt? Okay, I hope there is no doubt. And in case if it is there, after completion of this explanation, you can ask me the question. I represent the electron originally where it was. So here it was in what? The d orbital. So problem in front of people was geometry is square planar, but hybridization is not a dsp2. How to describe that? It was a big question. Then one option came in front of the people that will it be possible that this one s orbital, second orbital as a p orbital, third orbital as a p orbital, and fourth orbital, here see, after that the orbitals will be there 1 2 3 4 5 d orbitals. So one of the d orbital will be involved. So this d orbital, these two p orbitals, and one s orbital, can they combine? Means leading which kind of hybridization? Sp2d. If sp2d hybridization, then also geometry will be square planar. So we are discussing this sp2d hybridization. Our previous attempts, general knowledge attempts of sp3 and dsp2 hybridization found to be not correct. Attempt to describe the hybridization in the copper as sp2d is correct one. Now let me describe this sp2d hybridization. Our example is copper ammonia complex. In that central metal ion is copper plus 2. I am writing now the only outermost electronic configuration. Here d orbitals, 9 electrons. After that d orbital, there is a s orbital. After that s orbital, there are p orbitals. After those p orbitals, there are d orbitals. See, for hybridization, there's a need that orbitals should be of similar energy, nearby energy. Then the mixing is possible. So which orbitals those are? Here it is the 4s orbital. Here in 3d orbital, 9 electrons are there, 4p orbital and 4d orbital. My point of interest here is sp2d hybridization. So which orbitals will be involved? This s orbital will be involved. Out of those three, 2 p orbitals will be involved and one of the d orbitals will be involved. Let you know the names of orbitals also. S orbital, there is only one orbital spherically symmetric. About the p orbital, one orbital is px, second orbital is py, and third orbital is pz, or whichever the x and y components are there, those will what interact here during formation of the sp2d hybridization if we are considering a plane in the x and y axis. And this d orbital, first orbital, is x square minus y square orbital, about which we are discussing. Next orbital is a dz square. It is just for your information now at this moment. This orbital is a dxy orbital. This orbital is a dyz orbital. And this one is dxz orbital. My point of interest here is this one for s orbital, 2 for p orbitals, and last one is a 4d orbital. So s orbital is spherically symmetric. Let me represent that orbital now. S orbital, spherically symmetric. Sphere. The px and py orbital, if I consider it is the x-axis, left, right, so it will be the px orbital. If I consider this as what the y-axis, up and down, upside and downside. So here px orbital also is there and py orbital is there. Here two different orbitals are there. It is better that I should represent them separately. So one px orbital, afterwards py orbital. Okay. Now I come to the d orbital. That's a dx square minus y square orbital. For your information, I represent here is x-axis, and if I consider the y-axis, then px orbital, as like px orbital, this dx square minus y square orbital will be along x-axis and along y-axis. It is our dx square minus y square orbital. If you see these all orbitals and if they combine, then the preference will be to align in xy plane because it is along x-axis, it is along y-axis, it is along x-axis as well as y-axis. So major orientation is along x and y axis, xy plane. So likewise arrangement of the orbitals will be there. If the four orbitals are there, then the arrangements can be how that I represent it. Here in case of the px and py, 90 degrees separation. Here in case of dx square minus y square, 90 degrees separation. And this s orbital is spherically symmetric. So during hybridization, what will happen? This s orbital, this px orbital, this py orbital, and this dx square minus y square orbital, all these orbitals will mix and they will give the four-lobed new orbital. That's our hybrid orbital. Let me represent that four-lobed d orbital. That's a Sp2d hybrid orbital. How can I represent that four-lobed d orbital? One lobe, I'm saying larger lobe, second lobe, third lobe upside, and here is a fourth lobe. Angle between this is 90 degree, and angle between px and py also was 90 degree. Angle between the lobes of dx square minus y square also was 90 degree. So these orbitals peacefully, effectively can undergo this hybridization. What's the name of this hybridization? Hybridization is Sp2d. So therefore arrangement is square planar. Now let me explain it by means of our actual example. Yes, up to your concept clear, students?
Yes, sir.
Yes, sir.
Yes. Our example is Cu and H3 4. It's a coordination compound. Charge is 2 plus. Central metal ion present here is Cu 2 plus. Its electronic configuration is 3. Of course, argon will be there. After that, 3d9, 4s0, 4p0, and 4d0. In terms of block diagram, if I were to represent, then 1, 2, 3, 4, and 5 d orbitals, 3d orbitals. It's a 4s orbital. Here 3, 4p orbitals are there. Here 1, 2, 3, 4, 5 d orbitals are. Here 9 electrons. I am representing first electron, second electron, third electron, fourth electron, fifth electron, sixth, seventh, 8 and 9. So it is unp electron is there. In 4s orbital no electron, 4p orbital no electron, and 4d orbital no electron. Here this 4s orbital, 4px orbital, 4py orbital, and 4dx square minus y square. These orbitals only will overlap to give Sp2d hybrid orbital, which is square planar. And in those hybrid orbitals, electrons from ligands will come. Which ligands are here? Ammonia. What is the speciality of these ligands? Ammonia remains with lone pair, 2 electrons. And those 2 electrons, if I represent by cross mark, here is 1 electron, second electron, it's a lone pair. So lone pair from 1 ammonia will come here after hybridization. When they undergo hybridization, then other lone pair will come here, third lone pair, and fourth lone pair. So the lone pairs will come in those hybrid orbitals. Which are the hybrid orbitals? Sp2d hybrid orbitals, and the geometry will be the square planar. So how can we explain that? See here. Now it's the third point, the structural arrangement. That hybrid orbitals, how can I represent? Say it is a one lobe, opposite lobe, lobe upside, and lobe downside. It is our Sp2d hybrid orbital. This will form bond with ammonia. So each ammonia is with lone pair, and that lone pair here is lone pair, which is donated here toward the central atom or ion, that is a copper plus 2. Here also second ammonia is there, which has the lone pair, which is donated to copper. Here third ammonia, which has a lone pair, donated to copper plus 2. Fourth ammonia, which is donated to copper plus 2. So structure is square planar. Copper will be at center, and let me represent the square. At the corner of that square, there will be the ammonia molecules. Here is one ammonia, second ammonia, third ammonia, and fourth ammonia. Charge on copper is +2. Charge on ammonia is 0. So total charge on the complex, it is very important. It is not fair to represent the diagram of structure in this way directly. Charge on that complex will be +2, and that is because of the copper. It is a structure of copper ammonia molecule. I repeat. Then if you have any doubt, you are free to ask. Our point of interest is to discuss the copper ammonia molecule. Here, different possible hybridizations are sp3, means this s orbital and all these 3 orbitals will overlap to give tetrahedral structure. Problem for tetrahedral structure is angular separation, 109 degree. That much molding, that much change, that much distortion, that much deviation that p orbitals should do, which is a troublesome task. It's like a yogasana for that p orbitals. But if square planar, then easily it can arrange, because in square planar 90 degree separation, so more efforts will not be needed, investment will be less and profit will be more. In tetrahedral, investment will be more and profit may be relatively less. Molecule want more profit, proper business mind. So here tetrahedral hybridization is not suitable because that much amount of energy is not coming, okay, or less profit will be there. Second hybridization possible is Sp2d that I discussed, where the electron from or the empty orbital, that's s orbital, is two p orbitals and one d orbital, where x and y components are there more, because xy plane for the square we are considering, will undergo Sp2d hybridization and resultant structure will be square planar, and it is absolutely correct. Third possibility, possible, which possibility is there, which hybridization is possible? It is DSP2, which also will result square planar geometry. But what we need to do for the DSP2 hybridization, this d orbital should be free. This d orbital should be available. To make it available, we have to remove this electron. We have to excite this electron in higher orbital, which is not fair consideration. That's the excitation of the electron. Therefore, DSP2 is not a fair possibility for copper ammonia molecule formation. Many where this wrong hybridization is explained there in the book. But the correct hybridization, that is what? Sp2d. So students, I discussed today Sp2d hybrid orbitals and square planar structure possible because of that, and for that example is copper ammonia complex. It's only one topic I had covered. Similarly, if you work, I give you the example for the homework. Listen carefully. It is the homework for you. One complex I give it to example. It is of manganese, MnCl5-3. You have to find hybridization involved in this MnCl5-3. Total 5 bonds are there. So 5 bonds. So one may think it can be Sp2d hybridization, which is not. One will say it may possible Sp3 hybridization. This also not. Then you have to find out which is the actual hybridization. As I discussed, Sp2d hybridization. Likewise, here interesting hybridization is there, which will prefer. See, if you consider the 5 bonds, then generally what you consider trigonal planar arrangement, trigonal bipyramidal arrangement, trigonal one upside and one downside. Such 5 bonds as like phosphorus, one chlorine bond, second chlorine, third chlorine, fourth chlorine, and fifth chlorine. Such bonds you have considered. So the TBP structure was expectation for that new hybridization, but that TBP structure is not there. Then which structure is there? Square pyramidal structure is there. You have to consider square as a base and one apex, one bond. So that's square pyramidal. Here first bond, second bond, third bond, fourth bond, and upside fifth bond. You can consider the 4 chlorides at the end of that square pyramid, corners of the square pyramid. And manganese you can consider manganese +2 at what? Center. So to resolve that square pyramidal structure, you have to consider this hybridization. What is that hybridization? That you have to find out. An explanation of that hybridization by means of this example you can consider MnCl5-3. You have to work for that. Yes, students. Now, whatever I wanted to describe, that I described. Now it's your turn to raise the questions. If any question is there, feel free to ask the question. Okay, if no question, then say no question loudly.
No question.
No question.
No question.
No question.
No question.
No question.
Very good.
No question.
So, I sum up discussion. Today, I discuss the 4 possible ways of hybridization for 4 bonded compounds. First was Sp3. Second was DSP2, third Sp2d. All three are different hybridations. Out of that, I discuss here Sp2d hybridation with example of copper ammonia complex CuNH3 4 2 plus. And as a homework, I had given you one molecule, that's a MnCl5 minus 3. You have to find hybridation for that. I told you hybridation there is not Sp3d, not DSP3. Then what is actual hybridization? That you have to find out and you have to describe that. Yes, students. So if today's concept is clear, shall we stop? Yes, Gaurish, your hand is raised. Any question? Yes, very good. Ask question, Gaurish.
No.
Yes, Gaurish. What's the problem?
By mistake, sir.
Okay, no problem. Okay, students, then I stop the recording and I declare today's lecture is over. You can quit now.